Okay, so in this video we're going to learn a further application of why differentiation is important. As we know, differentiation can tell us the gradient function, and therefore the gradient of any point on a given curve, because as we know, on a curve the gradient is not always constant as it is on a linear expression. So if we take this curve in question, indicated here by the graph, this is the equation y equals x cubed plus 3x squared minus 4x plus 2. And the question is asking me to find the equation of the tangent and the normal equations at the point P, which is 1 and 2. So if I'm looking on my graph here and I locate the point 1, 2, so we're talking about this point here. So the question is asking me to find the tangent, so as we know the tangent just touches a curve at one point only, just like you know from your circle work. And also it's asking me to find the normal, and remember the normal is always the perpendicular line to the tangent. So in order for us to construct these line equations of the tangent and the normal, we need to know what the differential is, the gradient is, of the curve at that given point. So let's start by differentiating our curve. So dy over dx equals the 3 comes down 3x squared plus 6x minus 4. And then we're going to say at point P, so at point P, our x value is of course 1. So we can sub in just from our line equation and our line geometry work, m1 equals, and we're just putting in that 1 in there, so 3 times 1 all squared plus 6 times 1 minus 4, which gives us 3 plus 6 minus 4, and this of course will give us 5. So my gradient of my tangent equation is m1 equals 5. So let's reduce this down and finish this off, and just like you were doing with your line geometry then, I have y equals 5x plus c at my point P, which is 1, 2, and then it's just a case of finding c. So I'm going to sub those numbers in, so I get 2 equals 5 times 1 plus c, and therefore c must equal minus 3. So my tangent equation of this curve at the point 1, 2 is y equals 5x minus 3. So what I would do in an exam, I would draw a little box around that, and I would label that tangent P1, 2. Now let's use the differentiation or our result that we've just found in order to find the normal equation. So as we know, m2 equals minus 1 over m1, because remember the normal line is perpendicular to our tangent equation. So therefore my m2 equals minus 1 over 5. So back to line geometry as normal, y equals minus 1 over 5x plus c at the same point P, 1, 2. Plug in the numbers, I get 2 equals minus a fifth plus c. Let's tidy this up. We need to make the denominator the same here, so I can plus those two together. So that would be 10 over 5 plus 1 over 5 equals c, which of course implies that c equals 11 over 5. Therefore, just to finish this off, I get y equals minus a fifth x plus 11 over 5. I draw a box around it like I would in an exam, and I would just write normal P1, 2. And we're done. Okay, so now we're going to look at something called stationary points, which occur on the curve when dy over dx equals 0. So essentially, when our gradient is 0. So if I was to draw something like this, you can see if I'm starting from here that my gradient is positive, isn't it? It's positive it keeps going positive, and then suddenly there's a flat, isn't there? So at this point, if you imagine, say this is a ball being thrown up in the air, for instance, you imagine that the ball is travelling up and up and up and up and up, and then suddenly, just before it's about to fall back down, we have this stationary point here where it's held in stasis, and then it would start coming down. Do you see? So here we have negative gradient, negative gradient, negative gradient, negative gradient, goes all the way down, and then suddenly we have another rest here. So this must be another stationary point, because dy over dx equals 0. And then positive to positive to positive, flat, dy over dx equals 0 here, doesn't it? Negative, negative, negative. Okay, so what you guys need to know is that there are 3 types of stationary points. There are what's called maximums, minimums, and inflection points. So, maximums and minimums are also called turning points. So, the order is, we have stationary points, which means dy over dx equals 0. We then have 3 types of stationary points, which are maximums, minimums, and inflection points. Maximum and minimums are called turning points as well, and that is because, as you can see, going on this graph here, we have our gradient going from positive to negative either side of our stationary point. And the same with the minimum, which you can see here, our gradient is going from negative, negative to positive either side of our stationary point. So you can see it's called a turning point because we have a change in sign either side of the stationary point. Whereas a point of inflection can look like so. So there's my stationary point, dy over dx equals 0. Our gradient is positive, positive, but it doesn't change, does it? Because here it's still positive, positive, either side of the stationary point. And similarly in the negative direction, so negative, negative, inflection point here. Okay, so that's the difference. Maximums and minimums, the gradient changes sign either side of a stationary point. Inflection doesn't. Inflection continues. The actual definition of a point of inflection is when the graph turns from concave to convex, and it's that point that occurs. But for us, in our studies at this point, we are still always talking about inflection in terms of relating it to stationary points. And it's the same from going the other way around, so convex to concave. Okay, that's what inflection means. Now if I'm looking at this graph up here, which I've indicated, which is the graph of y equals x to the power of 4 plus 3x cubed, we can see that here we have a minimum because the gradient is going negative to positive and the stationary point is there. So this must be a min. And here we can see we have a flat, which must be our stationary point, dy over dx equals 0. And you can see that the gradient is going positive and then continues going positive after the stationary point. Therefore, this must be a point of inflection. Now, in the next slide we're going to see how we identify stationary points and how we can find them. Okay, so what we need to do now is we need to know how to identify our stationary points and find them. So, if we take this example of y equals x cubed minus x squared minus x plus 1, we can use this to try and find our stationary points. The reason why we're doing this is because sometimes we may not have a graph, and it might be obvious from a graph where the stationary points are, but we need to prove this algebraically, okay? And this is very useful for very complex functions. So, it's quite a mechanical process, but this is what we're going to do. The first step, we're going to differentiate this. So we get 3x squared minus 2x minus 1. We're then going to set it equal to 0, because remember, at stationary points, dy over dx equals 0. Okay, so you must write this down, because this gradient function does not always equal 0 at all, does it? It's only at stationary points. So it's very important to write that down. Let the examiner know why you're doing what you're doing. Then we're just going to factorize this, because we're trying to find the coordinates of our stationary point. So here I can tell that x must equal minus a third and x must equal 1. So step 2 is to write a conclusive statement that y has stationary points at, and then I just need a set of coordinates, don't I? So minus a third, bracket, and x is 1, bracket. Do you see we're missing the y values? So to get the y values, all I'm going to do is I'm going to plug my x values back into my original equation, because remember here I have y equals and I'm trying to find y, and if I put my x values back in, I get y equals 32 over 27, and I would get y equals 0 at x equals 1. So there I have my stationary points now, but it's not good enough to just leave it like this. I now need to classify them to know whether they're max minimums or inflection points. So this is where we have step number 3, which is our check nature step. Now, to go into a little bit of detail, I'm going to differentiate my y twice. So this is meaning that I'm differentiating my gradient function, remember this is my gradient function, again. The reason I'm doing this is because I want to know if these are max mins or inflection points, sorry. So if I find that d2y over dx squared is less than 0 at my x values, then that would produce a maximum. So remember, a maximum goes from positive to negative after the stationary point. Or d2y over dx squared could be more than 0, which would indicate it's a minimum. Or d2y over dx squared could equal 0. And this is where we would require further investigation, which will be in another video. Okay? So, let's do this to our curve. So if we go and differentiate my gradient function, which is 3x squared minus 2x, I would get 6x minus 2 at, let's pick the first x value, at x equals minus a third, my d2y over dx squared would equal minus 4, which of course is less than 0, so it must give me a maximum at my stationary point, minus a third, and 32 over 27. Okay, so maybe put a box around that. There you go, you've classified your first stationary point. Now let's do the other one. So we get d2y over dx squared equals 6x minus 2 at x equals 1 this time, which means d2y over dx squared would equal 6 times 1 minus 2 is 4, which is greater than 0, therefore we must have a minimum. And therefore my stationary point 1 and 0 gives me a minimum. And we're done.